So the backstory to this is that about 10 years ago, I, together with Dag Normann, published this book on higher order computability. And then about 2 years ago, to my vast surprise, I was contacted by Springer with an invitation to produce a second edition, expanded, more pedagogical, more space to applications. Which I was very surprised about, but absolutely delighted to do, because I can see all the things with hindsight that you know, I wish we'd done in the first edition, better than the first edition. So the second one's going to be much better than the first one. So I thought that while this stuff's sort of in my mind, and I've been thinking about how to explain it, how to present it, I may as well give some talks on it. So if you know, if anyone's interested in more details, I'm delighted to share drafts of the relevant book portions. And if that resulted in, you know, suggested improvements to the content, that would be a really good outcome. I'm also willing to make this a little bit dynamic in the sense that I'm prepared to be influenced. I have a plan for the lectures, but I'm prepared to be influenced to some extent by what people are interested in. So if at the end of this lecture you want to tell me, you know, I'd like to hear more about that, or less about this, do tell me. I may be able to accommodate that. I've got far too much material anyway, so we'll see kind of how we get on. But that's the nice thing about leaving things a bit fluid. Okay, so we're going to be looking at some computability theory for higher order functions. So for these talks, we're basically going to be looking at the types you can form from a base type of natural numbers with an arrow type constructor. So you can have functions acting on functions, and so on. It's roughly split like this. So in the first two lectures, we'll be looking at languages for total functions of higher type, and principally Gödel's system T. And in the second one, languages for partial functions, sort of in the Haskell or ML tradition, mainly Plotkin's GCF. So for as long as I've been in LFCS, there's been a sense of a bit of a culture divide between the research tradition that works on the first of these and the second one. That's to some extent reflected in this split here, but I hope as well there'll be some kind of unity to the course, and I hope to show they're not two completely disjoint subjects. Okay, so plan for this lecture. I'll first tell you what System T is. I'll give you a modern definition. Mention some motivations for being interested in it, and look at the history, what Gödel introduced it for. I think this is interesting and also worth seeing, because even if Gödel's motivations, which are kind of foundational, are probably different from the motivations of most people today, it's illuminating because it sheds light on what it is that this stuff's good for, what kinds of things it potentially buys you. So we'll spend some time today to look at that. Then we'll look at some sort of meta theorems about System T. And I want to emphasize the power and versatility of the method of logical relations as a proof technique for proving a variety of stuff. And then we'll actually look at some stuff that you can do in System T, so actual programs you can write that might be a bit surprising and counterintuitive. So I probably won't get too far with that today, but we'll make stuff. And then lecture 2, we'll talk about the dialectical interpretation, which is more on what Gödel was actually playing. So what is System T? It's a simply typed lambda calculus with the types I've told you about, and just these constants. So we've got 0 and successor for the natural numbers. And for each type sigma, we've got this recursor. So pointy thing, or we'll just assume the mouse, because then we want. Oh, I just use the mouse. Yeah, that's it. Okay, so if you want to produce a function from n to type sigma, it's enough if you give a starting value of type sigma and a way of getting from your previous value, your value for n, to your value for n plus 1, where you're also allowed to use what n is. So this is basically a kind of primitive recursion operator for a general type sigma. If sigma is itself the natural numbers, we get usual primitive recursion. We have the general list. So another possibly helpful intuition is to think, broadly speaking, you can think of System T as a higher order language which sort of embodies the power of something like for loops. So bounded iteration. So you say in advance how many times you want to do this iteration for. So supposing sigma represents the sort of mutable state involved in your for loop, you come into it with an initial state, and then you give a number n, you go around this loop n times, and you end up with a final state. So bounded iteration, but definitely not unbounded iteration as in while loops, because that would let you open the possibility to things not terminating. So with for loops and nested for loops and stuff, you're guaranteed, however many times you nest your for loops, you're guaranteed to get termination. So that's one possible reason for being interested. So again, from a modern perspective, which wasn't how Gödel said it, we've got a reduction relation generated by usual beta reduction plus these two rules for the recursor, which do what you'd expect. So for 0, we use our starting value e, and for the successor event, I actually mean that to be a no, that's all right. That's all right. Okay. Okay. Nice thing about this language is it has a very easy classical set theoretic semantics. So it really is okay to think of n as denoting a type of natural numbers, and sigma arrow tau is just a simple set of all functions from sigma to tau. We don't need any domain theory. Sorry.
Phil has a question. Is that okay?
Yes.
Phil, can you unmute?
Yeah, so you've written here, rect sigma is like primitive recursion. I can see why you say that, sort of looks like that.
Mm-hmm.
But as I recall, John Reynolds chose for system F how to define Ackermann's function, which is famous for not being definable with primitive recursion. I would guess you could do the same in system T. Am I correct about that?
Okay, so to define Ackermann's function, we use rec, but rec not at type n, but at type n arrow n. So Ackermann's function isn't primitive recursive in the normal sense, but is primitive recursive in this generalized sense. So you get genuinely more power by having the primitive recursives at higher type. Does that answer the question?
Right. So rec gives primitive recursion when sigma is n, but if sigma is something else, like higher order, then it can give you more than primitive recursion.
Okay. Yeah, it gives you a generalization of primitive. I'll put primitive recursion there in scare quotes. It's a natural generalization of primitive recursion to arbitrary.
Okay. So I understand why you said primitive recursion, but there's a sense in which it's misleading. I wanted to just check if I was right about that. And fortunately, I am. I'll let you get on.
Yeah, thank you. Thank you. Okay. Yeah, you really can think of this classical set theoretic semantics. You don't need domain theory or anything like that you might use to interpret other languages. So that's a plus. So it's quite easy to check that this operational semantics is sound. The demonstrational semantics is sound for the operational semantics in the sense that if n reduces to a numeral n, and this just abbreviates the n-fold successor of 0 numeral, then m denotes n. The converse of that is true, but definitely not trivial. We'll come to that, but just for now, to get the big picture, we'll take this on trust. So now, picking up on what Phil said, we can consider the sublanguage, which was called T0, where you restrict your recursor just to type n. That's the wrong sort of n there. Just noticed in mind. So if you do that, you get the usual primitive recursive functions on the natural numbers. That's not too hard to show, but I won't delay over that. Okay, so it's sort of a powerful generalization of primitive recursion to higher types. Okay, so so we can see now that this language defines a good class of total computable functions on the natural numbers, including primitive recursive ones, but also more. It is also equally easy to see that it doesn't define all total computable functions on the natural numbers. Quite a simple diagonal argument to show that one thing you can't write within system T is an interpreter for system T terms itself. That's easy to show. So we get a certain good chunk of computable functions, total computable functions, but not all of them. So that's the bargain you make when you choose to work with a language for total functions. Okay, it means you simplify things, you never have to worry about termination, but it's inevitable because this diagonal argument is very, very general, that you're never going to capture all computable functions, all total computable functions. You're just going to capture a certain chunk of them.
But John,
Yeah.
are there other sort of natural classes of functions that you can't specify here that don't have that flavor of, well, going through a diagonalization argument?
Right. A class of total functions
That cannot be expressed in system T, but and yet.
well, I mean, you could say the class of all total computable functions. But the point is, whenever you've got any sort of language with a decidable syntax.
No, I realise that. I was just wondering whether there's any other construction that gives you counterexamples.
I'm not aware of any. I mean, you know, if your language definition, you know, either your language definition is sort of effective in this way, or it's not.
I don't think you get such examples in the wild. You have to search for examples by means of some computability argument as well.
Yeah. Okay, so one reason for being interested in system T maybe is it serves as a prototype for a lot of other things. So in the decades since Gödel's work, people have proposed a lot of other systems that sort of have this flavor of being a language for total functions. Some of them are much stronger than system T. So we've got Gödel's system F, and we've got various systems with what we would nowadays call inductive types, although they didn't think of them that way in the old days. Those are extensions where we extend the type system. We've also got one where you don't extend the type system, you just add a more powerful operator, bar recursion. And this one I may be saying something about in lecture 2, because I think it's fascinating. So these are all sort of modeled on system T, if you like. But also you can go downwards. There's sort of weaker languages with the same flavor. And so Crick and Urquhart have this higher order language for feasible, as in sort of polytime functional, sort of polytime analog of system T, if you like. And that's only a small selection. There's many, many other things that have been systems that have been looked at with this flavor. And all the ones I mentioned here and others also have, I've presented them here as computational systems, but they also have close links with logical systems, and we'll be looking at those. So we'll be looking in some detail at system T, and in the next lecture at its links with, for example, Peano arithmetic. So that's a relatively simple prototype case that's worth looking at. Things are fairly clean. But then the idea is that sets a pattern, and many of the core ideas that you can understand in that framework can then be rolled out to some of these other situations. So this is one reason it's maybe worth studying system T as a relatively simple arena for grasping these ideas. There's an excellent survey about this stuff.
John,
Question?
Yes,
if you can just go back to the previous slide.
sorry.
So you mentioned Kreisel 1964 and Pfefferman 1970. I thought, oh, I should know those, but I don't. So I went to Google Scholar and typed in Kreisel 1964, but it didn't find the paper. So can you give me another keyword or two to put in to find the paper?
Oh gosh. Could I do it
offline, I think.
Could I do it offline?
In the chat.
Absolutely.
Yeah, thanks. Yeah. The reference I'm familiar with for this stuff is the Trollstra 1973 book. So there's a chapter by Jeff Zucker in that, which is what I know this material from.
I see. Okay.
Yes.
I'll write to you. Thanks.
Thanks. Okay. So so that was one kind of motivation. So for another kind of motivation, let's look at what Gödel was trying to achieve. So this has its roots in back in the 1920s foundational project of Hilbert and other people, when people were very worried about which mathematical statements, in particular mathematical statements involving infinity in some way, whether they had any real meaning or not. And they were trying to put the whole thing on a good foundation. So there's this finitist school, which imposes a severe restriction on the kinds of mathematical statements that we accept. So as a broad first approximation, we accept a statement as meaningful only if it makes clear, testable predictions about the outcomes of certain calculations. So let me illustrate that with an example. So supposing you've implemented a crypto system of some sort, you want to make some kind of guarantee about it. One thing you want to know about a crypto system is if you start with any message M and you encode it, then you decode it, again, you get back your original message M. Okay. So we think of M here as being allowed to arrange over, potentially infinitely many possible messages. But this makes, a definite claim, a definitely meaningful claim about your system, which could turn out to be false. So you could make this guarantee. You could say decode encode M equals M, or your money back. Okay, that would be a sort of guarantee. So you're sticking your neck out and you're saying something that could be refuted. So we accept these kinds of assertions as meaningful in some way. But a non-example would be just the statement, just taken by itself, the statement, there are infinitely many prime numbers. So the point is you can do calculations to test if particular numbers are prime. 13 is prime, 15 isn't prime, 17 is prime, and so on. You think of those calculations as something like observations that you can make. And the point is, however many observations you collect, okay, it will be perfectly compatible with those observations to believe that there are infinitely many primes, and perfectly compatible with them to believe that there won't.
Sorry, when you say this is a non-example, do you mean it because of how the statement is syntactically shaped? Because I can think of an equivalent statement saying, give me any prime number, I will give you a bigger prime number.
Yeah, we'll come to that. Just look at this on the face of it, without any additional. You're absolutely right, but we think of this without any additional information. The point is, this is something that couldn't be confirmed or refuted by any finite number of calculations. So the idea is that from a sufficiently hard-nosed, skeptical viewpoint, you could say, well, is this actually saying anything at all about anything? That's the idea. If you're kind of intrigued by the philosophical side of it, of all this, you might be interested in my other book. Okay, and it's widely agreed that the sort of core of finitism is quite nicely captured by this formal system of primitive recursive arithmetic, uses Golem.
I'm sorry, John, could I follow up on the questions just asked?
Yeah.
You gave us an example of something that syntactically can't be expressed in a finitist way, but in fact, it's fairly easy to think of a finitist way of expressing something that's equivalent. Are there any standard examples of things that cannot be expressed in a cannot be expressed in a finitist way, so don't have an equivalent finitist way of saying them?
So when you
are there any standard well-known ones?
Yeah, yeah. So if you go further into number theory, so I think like van der Waerden's theorem or something like that. There's various combinatorial theorems where either it's not known or it's known that you can't find a finitistic witness for the truth of the statement. They do exist, yes.
Okay, but you can't tell us one off the top of your head.
If one occurs to me that I can summarize quickly, I'll come back to it. I'll let you know.
Okay, that's fine. Thanks.
Okay. Okay. So think of a system where we've got. Let's give ourselves an atomic symbol for every primitive recursive function and relation on n. So we think of primitive recursive things as things we can compute unproblematically, because primitive recursion is the very nature of natural numbers gives you the idea of iteration, primitive recursion, something like that. You build up formulae using the propositional connectives. You don't allow quantifiers. We do allow formulas to have free variables in them, and you can think of these free variables as implicitly universally quantified. So it's as if there's a for all at the far left of, like I've written this for all here, It's as if there's a for all at the far left of the formula, but for the purpose of the logical rules, you don't actually want it to be that. So, so it's quite widely agreed that this system captures the core of what's finite-statistically acceptable. Now, Hilbert wanted to prove the consistency of something bigger, like Peano arithmetic, within the system PRA or something like it. And as we all know, Gödel showed that this can't be done. But Gödel was interested in the idea, and his motivation in his next decades was to try to give an interpretation of Peano arithmetic that was as close to being finite-statistic as possible, but was somehow within the spirit of finitism, even though it couldn't be captured in PRA. Okay, so this maybe picks up on what's come up so far. So for example, in PRA, you can prove the theorem for all n, there exists a p bigger than n such that p is prime. And as we've seen, this isn't a finite-statistic statement as it stands. We've got these quantifiers here. But let's suppose we could extract from the proof, as indeed we can, a specific function capital P such that P produces a prime number bigger than any given n. So once you've got hold of this P, you can actually write this statement here. And this now is a finite-statistic statement, implicitly for all here, because this is something that makes a prediction. You know, any number I give you, you can check this whether this comes out true by calculating your P of n and checking that it works. So we can give sort of finite-statistic content to this statement. We may also give finite-statistic content to this statement that can be extracted from the proof in PA of this. Now, it might seem plausible that you can do that if we have a constructive proof of this formula, but of this theorem. But as we know, Peano arithmetic is a classical system, also allows non-constructive reasoning. So what if we had a non-constructive proof of this theorem? Would you still be able to extract from it a function p that does this? Maybe not so obvious, but that's what Gödel's aiming for. Okay, so here we've just got an ordinary function p on the natural numbers. But now the idea is that if you then move up to more complex formulae, for instance, we've got a formula of this for all exists form on the left of an implication, maybe applying another one, and you try to extract some kind of operation from this, then what you're likely to get is some operation which takes as its argument a witness for this for all exists thing. So that would be, it would take as its argument a thing like this p here and produce another thing of the same type. So we might expect a witness for a formula of this shape to be a second order operation. So if we pursue this route, we find we're naturally led into the realm of higher order functions, not just first order functions. So Gödel's idea calls for some sort of extension of primitive recursive arithmetic, where terms, including and variables, can be of any type sigma. So still no quantifiers, but without variables of any type sigma. And this was in fact the birth of system T, which was given as a suitable system for expressing this. Okay, so I'm old-fashioned and I like blackboards. So here's diagram of the big picture, just to show sort of how things fit together. So what Gödel did, as we've seen in the last slide, is he sort of swapped. He found a way of getting rid of quantifier complexity in favour of type complexity. So here's the sort of big picture. We start with our primitive recursive arithmetic, which is our finite system here. And we can think of at least 3 different ways to extend it. One is we can extend it with quantifiers for all that exists. if you're happy with the idea of quantification over the natural numbers, that takes you up to the level of Peano arithmetic. So you can increase the logical complexity of your system, or you can stick with just the propositional operators, just add in higher types. So we enrich our language into a sort of higher type version of primitive recursion. So we have system T as our term language, and we have equations between system T terms. We have the propositional operations. We still don't have any quantifiers. I've informally called this PRA omega here. It's a sort of higher order extension of PRA. That's a bit dangerous. That's not its official name, so I'll put it in quotes, but it's not a bad place to start with. So we can increase the type complexity, or we can stick with just the plain natural numbers, still not add any quantifiers, but add more induction power. So rather than just ordinary induction on the natural numbers, we can represent certain ordinals, certain transfinite ordinals, as natural numbers, and we can add a rule that lets you do induction up to certain ordinals. So sorry if this isn't so clear on the slide, but this is here we've got the ordinals omega, omega to the omega, omega to the omega to the omega, and sort of continue those. And then the ordinal known as epsilon 0 is the limit of these ordinals. So for any ordinal less than epsilon 0, you'll be able to do induction up to that ordinal. So we can increase either the logical complexity or the type complexity or the ordinal complexity. And now the point is, you can trade off. Sorry,
It has a question.
yeah.
The corner of the triangle you've called PRA to the omega. Could that also just be called system T?
Okay, so in Gödel's nomenclature, yes, you could, because Gödel introduced T as an actual language of logic and equations between terms. I've introduced it as just a term language by itself. But if you have the term language plus equations and you can throw in basic propositional operations, you want basic propositional operations to be able to have like the modus ponens rule and things like that. So yeah, if you interpret T as being a simple logic based on the term language rather than just the term language itself, then yeah, you could call this T. I bet, yeah. Sorry if I didn't make the best decision there. So.
And does PRA plus transfinite induction have another name?
No, it would just be abbreviated to TI less than epsilon 0 rather than transint, but that would be the standard name for it.
Okay.
Yeah.
Thanks.
Okay. Thanks. So the idea is you can sort of trade off any of these kind of complexity for the others. So as we've seen, what Gödel did is roughly he showed how you could eliminate logical complexity in favor of type complexity. And in some sense, 10 years later, what Tate did was go in the other direction. So in other words, it showed how statements about evaluation of system T terms can be expressed in Peano arithmetic, and you can prove things about them, at least any particular system T term, you can prove things about them there. On the right-hand side of the picture, we've got the work of Gentzen, who in fact looked at both of these directions. The downward direction from logical complexity to ordinal complexity, that's the idea of cut elimination. So Gentzen managed to eliminate the logical complexity in favor of basic language of PRA, but with a new transfinite induction rule that lets you do this. And you can do various other kinds of trade-offs between them. So in some proof-theoretic sense, all of these languages have the same strength. They all have the same consistency strength, for instance. But it's interesting that you can trade between them. So this is the big picture to grasp. And we'll be looking particularly at the left-hand side here. I won't be saying very much about ordinal complexity, though it may come up briefly.
John, when you say they all have the same strength, is that just the corners or are you including PRA in the middle? I'm guessing you're including PRA because Skolemization would let us
They're all much
do that.
stronger than PRA. Yeah, the corners all have the same consistency strength, but it's easy to prove the consistency of PRA in any of these systems. So for any of those outward arrows, any of the outward arrows from the center takes you up quite a lot. There's a big jump.
Oh, okay, so I thought that Skolemization would let us stimulate quantifiers in PRA, but I must be wrong. What am I missing?
Well, kind of, but but you need to go to. But that's what Gödel's. Kind of, if you're willing to go to higher types. But well.
Oh, I see. To do the Skolemization, I need the higher types which aren't in PRA.
Yeah. It's really, so it's maybe it's worth mentioning. It's not just the for all and exists. It's the implies. It's the implies in combination with for all and exists that really gives the trouble. Because if you've got a complicated formula, implies another complicated formula. That really, you can do quite a lot at first order. If you don't have implies, you can go quite a long way. But it's implies sort of explodes in power when you add for all and exists.
So just to fill in the history for me, PRA was defined by Skolem.
Yeah.
Presumably Skolem wrote about Skolemization. What was the result that he gave that we call Skolemization?
I don't remember, but I don't think it had it. But I don't think it was in connection with his work on PRA. I don't know. So I don't.
Okay, so that's just something separate, and I'll have to look it up. That's fine. Thanks.
Model theory of first order logic, and I think the concept of Skolemization came up there. But he certainly didn't consider. Yes. It was a rather different. It was a different bit of Skolem's work, I would say.
So, just for clarification, arrows here mean one theory can be interpreted in another.
Rough. In some cases, strictly that.
And then, but if not that, then what? What do the arrows mean otherwise?
Okay. So, for example, the Tate arrow there. That means yeah. I guess it can mean you can interpret.
I guess the different thing with the tape, you do the normalization inside system T, and then the transformation to piano arithmetic is trivial. Is that the idea?
No, you can formalize for any. Okay, I would maybe. Okay, if it doesn't mean a strict translation, it means something close. I should think about that. I just mean more loosely some way of trading one of these kinds of complexity. Well, fair enough. Okay. Yeah, it'd be worth nailing down whether you make that more precise. Okay. So the idea is these statements of system T, or what's called PRA omega, if you like. These have the form of quantifier-free statements. So it's like rather than just choosing numbers to filter as values for variables, you can choose system T terms for values of variables. You can still see them as making predictions. So like we were saying, for any closed instance of this formula, you can compute and you'll get an answer that comes out hopefully right. So we can indeed see statements of this language as in some way finalistically meaningful because they make definite predictions. But that presupposes you're willing to take on trust that any closed system T term you write down can be evaluated, that you can just hit a button and get the answer. As I mentioned earlier, that that's a big question. How do we know every system T term, closed ground system T term, can be evaluated to a new or coming back to that? Okay, the modulo that, you can see this as finalistically meaningful. However, I think most people would say it's highly doubtful that this renders the meaning of the original Peano arithmetic any clearer than it was before. So if you're someone who's, not happy with the idea of quantification over natural numbers, are you really going to be any happier with this whole world of higher order functions, anything like that? So there's a whole realm of higher order functions cries out for clarification, and it turns out that all reasonable ways of making precise class of higher order functions that you might be talking about require machinery that turns out to be just as complex as piano arithmetic itself. So it was generally agreed that this there's no real foundational gain in making anything clearer by doing this. However, it's certainly the case that this so-called dialectical interpretation, which is I'm going to talk about in more detail next time, it does achieve something because it shows that even apparently non-constructive proofs can have some kind of, you can extract from them some kind of meaningful computational context. So these proofs, they don't just live in a sort of platonic heaven isolated from the rest of the universe, but you can get something from them that you can actually compute with and get concrete results out of. And it's interesting that later variants of dialectica in this tradition have completely abandoned any pretensions at giving a foundation. They're giving things that don't even look plausibly like finitistic reductions in favor of these more technical goals of being able to extract non-obvious mathematical and computational information from proofs. We'll see some examples. But this whole area of starting with an existing proof and seeing what you can get out of it that's not obvious at first is known as proof mining.
Could you clarify what you mean that the non-constructive proofs have a meaningful computational content? Like, can you give an example or what computational content? What do you mean by that exactly? I don't.
Okay. Yeah. Well, it's a bit. So you can actually extract programs from the proofs such that come with a claim of what you will see happen when you run them. So there'll be an example. Sorry?
You have the prime number.
The prime number example is a very simple example. So, but that's perhaps not a surprise. That's not a surprising one. What's more surprising is when there are proofs that are definitely classical. You can
the prime number example is constructive, right?
the normal proof of Euclid's theorem would be constructive.
Yeah.
Yeah. So it's not surprising that you can get
a
function out of it.
You're saying that it's different. You're saying other type of proof there are more.
Yeah. So it's more subtle. So we'll see. So what the computational content would be typically, it would be, you get a program which sort of is witness for the fact that you can't refute this theorem. A program such that if anyone claims to give a program that refutes the original claim, it will produce a counterexample to their attempt. But it's some
Still be an example, but okay.
Yeah. It's hard to explain in a few words, but hopefully clearer next time. So I'll keep saying that until the last 5 minutes, of course. Okay. So anyway, we've seen a great deal hinges. So now let's turn, if we've got time. Okay, I'll keep going and then let's see how we go on. Great deal hinges on this property that for any closed term of ground type, you can there exists a numeral that you can evaluate it to. So evaluation, you've got some evaluation that will terminate it. So how might we prove this fundamental property? So if you want to prove something about a general term, pretty much the only thing that comes to mind is to prove use some kind of induction on the structure of term, because what else have you got to play with? There's two obvious problems with this. We're claiming here something about terms of closed terms of ground type. And if we want to reason from subterms to terms inductively, then a subterm of a closed term, well, first of all, it might not be a closed term because you've got lambdas within the term. Well, we could say this the other way around. It might not be a ground type, first of all. It might have subterms of higher types, and they might involve lambdas, so they will have subterms within them that might not be closed. So a straightforward induction proof of this claim isn't going to work. But this does suggest that we try to generalize the claim we're interested in to something that says something about arbitrary terms. So logical relations, which is a very powerful proof method, give a way to do this. So this is simple, but this has an enormous amount of power under the hood. So I propose to look at a few examples of this. Okay, so the idea is that for each type, we introduce a predicate or a relation, a unary relation, curly T, for terms of that type. So at ground type, we just say curly T of M says that M has the property we're interested in. It evaluates to a numeral. And then for a function type, sigma out tau, we say M at that type has property curly T. If for all, so this is closed terms, if for all closed terms N with type sigma with the property curly T, for all closed terms N of type sigma, if N has the property curly T, then Mn has the property curly T. So in other words, M itself won't break the property T for terms that already have them. So if Mn turns out not to have the property of T, that's not M's fault, it's N's fault. And then we extend to open terms by saying an open term has property curly T if for all closed terms N suitable to be substituted into it, if these the N's that you're substituting have property T, then so that's the substitution. So this just extends the condition we're primarily interested in to arbitrary terms of arbitrary types in arbitrary contexts. So we can now reasonably hope to prove by induction on term structure that for any term M in context of any type, it has the property T.
You missed the index on that T, but I guess you mean it has the type, whatever the type the gamma tells you it does.
No, it's.
It's
On
T of
point
gamma.
23.
Oh, it's T of gamma, right? I see.
Yes, yeah. Okay. And the headline is basically that works. So once you've got this far, you've done the hard bit, okay? And if you try and now work through this proof, it's essentially self-proving. You just follow your nose, you do the induction cases, and there's nothing very difficult. I've done the two least trivial induction cases there, and I won't talk through them because it's time to wind up. But basically, you've cracked once you've set up this logical relation. You've basically cracked it. The rest is just, I mean, it may look a bit complicated, but you are just unraveling the definitions and following your nose and doing the kind of obvious thing. So that's the basic method. And just to say, I've just said, we've just so far shown that any closed ground term can be reduced to a numeral. With a bit of more work, you can use the same method to prove strong normalization. So any reduction path you want to follow, you'll eventually hit a numeral, and in combination with the Church-Rosser property, which you kind of prove on the side, that gives you strong normalization. So, okay, so apologies that I've got through even less than I thought I might get through in the time, but I'll stop there, pause for questions, and then we'll have informal offline time afterwards. Is that okay? Questions?
Okay, I'm familiar with strong normalization. So can you just say what this proof has less than strong normalization?
Okay, this is what we call weak normalization. So
Yeah.
I've set up a reduction relation which is highly non-deterministic. You can use any
Yeah.
So all this proves is that there is some reduction path from your starting term M.
Right. In the proof, is there something significant less than the strong normalization proof in this proof?
You have to yeah, each of these bits of argument here would be about twice as long if you
All right, so you're telling me that you can consider just one reduction path in all of the cases.
If you want to prove strong normalization, you set up your logical relation differently. You say that if there was one there, you say TM means that
Oh, right,
it's strongly normalized. It's because we've just built in this weak normalization here. If you want to prove strong normalization, you set it up with strong normalization there. And then you have to work a little bit harder, but it's the same.
Okay.
Same idea. That's the most famous, and this is due to Tate. This is the most central, probably most famous single use of logical relations, but I'll maybe show you next time if you're interested. There are many other applications.
So take it strong normalization.
Tate did something in between. Yeah, it didn't do completely unrestricted. I mean, the ideas, the ideas there, but yes, it is a rather interesting class of possible reduction. I'm not even sure it was interesting, but rather curious. Yes. Okay, Kusha.
If I wanted to compare the power of this system T on kind of the, not on higher order stuff, but if I wanted to compare it in some way to, let's say, the power of Turing machines for total function. Now, obviously, with Turing machines, you can write things that are non-total, but suppose I placed some restriction on the Turing machine side in order to try to capture everything that system T could do as a total. Is there some way that I could do that just so I could?
I mean, you could if you put a bound on the you could put a bound on the runtime. You could do that, but the bound would have to basically say the bound. Anything that you can do in time bounded by a system T.
Well,
So
Yes.
you can't really. I don't.
can you do it anyway that's not self-referential? Can you say?
I don't expect. I wouldn't expect so. So if you want to other characterizations of. Yeah. There's other logical characterizations of the system T definable functions. But on the computational side, I think we'll basically come down to the original definition.
What does the T in system T stand for?
I don't think it stands. I don't think it stands for anything at all.
Why do you then?
Because Gödel wrote T in this setting.
Just following on from Kusha's question, you did have this triangle showing or claiming some form of equivalence between these different systems. Was that? You're not saying that these are entirely equivalent?
So a question came up earlier is how I mean, in terms of proof consistency strength, yes.
All right, but that doesn't necessarily mean that if I have a piano arithmetic statement interpreted as a program, mapping that onto a Turing machine, in order to characterize the restriction of Turing machines that allow me to do piano arithmetic, will that be the same restriction as the one for system T? Or would it be a different one?
I don't see how. I think you. Well, I mean, you can say that the provably. I mean, you can say that the provably total. This is a logical. You can say that the provably total. Yeah, the Turing machines that define total functions provably within piano arithmetic are the functions they compute are the system T definable ones.
Exactly the system.
Yes. Well, that's will be one of the results I may come to next time. But I would say that's a logical character. I mean, yeah, but well, okay, it's got a bit of computability in it, yeah.
Probably no more satisfying than the original answer, but you could use that to define your bound without referring to system T at all. Perhaps.
Provability in PA, yes, you could. Yeah. Good.
So there's certainly a gap between Gödel's paper and Tate's paper. It seems like using system T for that doesn't make sense if it isn't total. So the Gödel that conjecture that was total, or have a different proof? Or-
It didn't. Gödel really wasn't thinking of it as a computational calculus at all. Actually, the version I've given with the reduction systems, that's really Tate's take on it. So
was he thinking of
it doesn't. It does. I mean, one way of seeing that this is consistent is to prove a normalization result from it. To introduce a reduction system and prove a normalization. Because then you could say, yeah, there's the normal form for 0 is different from the normal form for 1, and so on. But yeah, it doesn't matter from the point of view of just giving the dialectical interpretation whether you have normalization, but that does matter if you want to make any claim that it makes a prediction. You're used to set make a prediction about anything.
It's always the button.
So what's coming up? So there's another application of easy application of logical relations to prove a context lemma. Then we look at continuity, which shows that every second order function final system T is continuous. And that's a nice logical relations. Omega plus 1 only logical relation proof of that. And then more sophisticated one. If G is definable in system T, then there's also a modulus of continuity function system for G is also definable in system T. So this is just a more advanced. Yeah. That's that. That's the end of the examples of meta theory with logical relations groups. Oh, and then on the other side, I mentioned a little connection with ordinals here. So a continuous function you can think of as a well-founded tree. Like if only you take your parts of the tree, and then when you've got enough information, you stop. Okay, and it's in fact, yeah. So just to make the connection with the ordinal complexity thing, any well-founded tree you can obtain from a system T term like this has height less than epsilon 0. That was the thing I thought I might indicate I could prove in lecture 3 or so, but might not. This is quite handy for proving that such and such can't be done in system T, because if you could use it to cook up a functional whose tree was epsilon 0 or bigger, then do it. So that's and then we have
Question? Can you compare trees in system T somehow?
compare
Can
trees.
system T be used to compare the heights?
These trees.
What can
I think you need. It's a very good question. There's a thing called stage comparison, which is in clearly computed. My feeling is no, or you'd have to work quite hard to set things up in a way that you.
You can encode trees in system.
In many ways, and this is one of them. So just as a second order functional. And you can encode. Well, that's yeah, and that's different. You can encode if you just want to encode a tree as a set of just a set of paths or a predicate on paths. You can define ordinals much bigger than epsilon 0. There. You can manage ordinal notations for much bigger ordinals. So that doesn't show you anything about our T much. But okay, then we have moving on to programs you can do. So Martin Escardo's strange thing that there are infinite sets such that you can write system T program to do an exhaustive search. You can implement existential quantification over these infinite sets. Yeah. And that only needs the power of t, in fact, only needs the power of t0 to do this. So this is just to show you there's surprising stuff that you might not be able to do. Then, yeah, there's a bit of, that's the proof of that, or the key of the construction of that. I have two exercises. So one is, I mentioned that you can't write an interpreter for t within t. You can write an interpreter for t0 within the next level up, t1. It's quite a good idea, quite a good exercise just to try and think how you do that. See where it is you use the power of the rec NRON.
Does the sentence there is actually a strict hierarchy, T not strictly included in T1 and strictly included in etc.
Yeah, it's a strict hierarchy. Sorry.
Does it mean that we can write an interpreter for Tn?
Yes, you can write, each one can write an interpreter for first order programs of the type lower down. And you get strictly more even first order functions as you go up. But yeah, this phenomenon, yeah. So none of these can write their interpreter for themselves, but each one can choose one from that.
Do they all have the same shape? If you write a meta program.
You could write a meta program that produced source program. Yeah. If you just do this exercise here, you don't see the full generality of it. But by the time you've written an interpreter for T2 and T3, you've seen all the ingredients. Yeah, that involves you could systematically write source texts for these interpreters parametrically in N, but that wouldn't, of course, because you can't interpret them uniformly, that doesn't help. I'm very fond of this exercise which came up in something I was researching. So this is something you might enjoy doing this. So let's say a tree is a prefix closed set of sequences of numbers. Okay, let's say we think of countable branching trees here. If it's a well-founded tree, there'll be a second order function that witnesses that. Namely, take an f, which is supposed trying to be a path through the tree, and it tells you the point at which that path exits the tree. So it's the least end such that this sequence of f0 to fm falls outside the tree. What it is to be well-founded is precisely that for every f there exists some such sequence. So you could say a second order function sort of embodies the well-foundedness of a tree if it has this. Okay. Now, given two trees T and U, okay, this kind, that just slightly informally, T hash U be the tree whose paths are interleavings of paths from T and U. So we use this tagging here to distinguish sort of moves in T from moves in U. So the idea is when we think of the tree where at any stage you can make a move, you can either go one step down your path in T or a step down in U, and you can do those in any order. And the moves are tagged, so that these are the moves in T, these are the moves in U. So I hope it's clear what I mean by this tree. Okay. So challenge, which is not that easy, to write a third order program. So these are second order functions. So write a third order T program, which given well-founded witnesses for T and U, computes a well-foundedness witness for T hash. Now the point is it's classically trivial that if both T and U are well-founded, then T hashes are well-founded, because any F is either going to mention infinitely many values on the T side or infinitely many values on the U side. So your lexic 101 or rather the tree. That's classically trivial. But is there some constructive content to this? So the challenge is to do this, resisting the urge to use any kind of unbounded search, which is what you're not allowed to do. So if anyone likes a hacking challenge, I can quite this gave me a lot of pleasure. So yeah. And what's interesting about it, you can do this with your bare hands, but you can also, once you know the dialectical interpretation, this is an example that of a program that can be extracted from the classical proof that I just mentioned, that if T and U are well-founded, then so is T hash U. Okay, so there's a classical proof, and you can extract from so that will give you a systematic way of arriving at a program which, with your bare hands, you can probably requires a bit of cleverness and ingenuity.
Okay, that one we did. So GREC is unique, it's the mainland. It's not a combination where you say a witness is GREC such that.
Yeah, you could say, and you could say any. If you didn't require this min-right, you just said GFL is some number n such that this is like true. That would be kind of good enough. That would be good enough. But you know, might as well say once you've got that, you can get a minimum n because you've just got finite many things to check.
Okay.
James.
So it's a question that follows from that discussion, which is, what are the relative strengths associated with extending T with, let's say, a single exception and the ability to handle it, or extending T with call CC, or extending T with the state monad?
These are really
so you can remember a number.
These are really good questions because most work on extending a language with such and such presupposes that you usually we start with a Turing complete language, I think, and then I would know a lot about what the answers to the questions were. But yes, it is interesting to see. Yeah. Yeah, so if you can find features, you're thinking about when you're adding features in ways that don't break totality, or?
Well, which actually don't change expressivity, but give you shorter or more convenient programs.
Yeah.
So I've got a bit of Friedman in mind for exceptions, and double negation elimination for core CC.
Yes.
We don't think that they should really change what's programmable, but things might be easier to program.
Yeah, you'll get a lot more observational distinctions between.
Oh, that I could believe, but at the moment we're just interested in computing.
If you're just interested in computing first order functions, right? Yeah. I would agree. Your intuition is you're not going to get more expressivity in that.
But has that been studied much?
Not to my knowledge. Good questions. This is you get so many good. You get too many good questions.
So you could just if you have a fairly loose notion of expressivity, you can just do a CPS translation for all of the things you mentioned, and they all translate into plain system T. So I don't know if that's what you're asking. Well, so in a classic move to say the person in the room can just do any particular action, you might do that, but it'd be interesting to explore the actual consequences of doing so. But that is not necessarily the system T. Certainly, just start with a. So that's why I asked the question for system T rather than as a generality. So when it came about from John's tree example, because one might imagine a classical tree in which you follow both paths and then you raise particular exceptions when you run out of elements and you need to jump into the other path to keep looking for longer and longer segments. And such a process, if it could be T interpretable by suitable shenanigans, might be a way of understanding a fast approach to programming
the WF witness the T hash.
I don't think in this case, because you can test, anything at each stage, you can test whether you test whether you're still on the true or not.
Okay.
And you're not doing anything, well, you're saying, if you look at my secret program, which I have in mind, it's not obvious. Could it be optimized with the help of a bit of
Or could it be programmed efficiently in an extension of T and then reinterpreted in T via a separate manipulation? Once you start talking about efficiency, doing the CPS translation doesn't necessarily help anyway. So I don't mean in terms of computational complexity. I mean in terms of cognitive difficulty. Stating the process. I mean, in both senses, it becomes a more interesting question.
Okay, variant exercise. Try and do this in 0 plus section, whatever, see if it's any easier.
Yeah.
And let me know. Yeah.
Sure.